Tuesday came out. I know some people are angry about the dispenser design, but don't be married to your ideas. That's number one. Number two is we're passing on kit plots. They'll be upstairs after lecture. So go up, you'll each have a tote. We'll get you some tape and just put your team name, team number on it. And speaking of team names, there are a couple of new teams now. There's Chicken Dinner, Thomas, Image Not Found, the Engine, and then a couple other ones I can't remember. But I thought I should plug, there is a prize for best team wiki, so definitely go write things in your wiki because you could win a prize. Laser cutting after lecture, just come up. You can have lunch if you want, or you can go do that first and then have lunch after. But that will be happening. We have MDF now. There's also a Git lecture that's happening for version control. I think Noah sent out the room number. And okay, cool. Juan will talk about, so when you get the kits, just be nice to the perks because we don't have enough money to replace everything. And so the lecture today is Juan, who will be talking about electrical, and then Eric will talk to you about Linux and commit. So, cool. Eric, see you at 12.
All right. Good morning, everybody. Let's get started here. So my name is Juan. I don't think I've been in this lecture room yet this week, but I am a current senior. So I'm finishing up my undergrad. 416 Aerastro, for those who don't know. Recently added 6.1 actually. So it's a fun time right now. But I actually haven't participated in Maslab as a student before. But over the past semester, and especially the past couple of weeks, I've been catching up on the important details you guys need to know in terms of electrical safety and generally just implementing the electronic skills that you need for your robots. So it's the electronics for Maslab, partially also electrical safety. So I'll start off with a small list of the things we'll touch on today. I'll sort of go quickly through the sensors and actuators because I want to prioritize battery safety and other ways to prevent things from blowing up when you build your robots. But we'll also talk about sensors and actuators, what options are sort of available for you, and if there are any more questions after that, you can feel free to reach out and ask. Okay. This is, since the slides are also supposed to be a reference for you guys to look on at your convenience on one of your machines or something, I think it's important to mention this here. I'm just using these symbols throughout the slides to indicate little points that are general recommendations, like strats for designing your robot, what to do. Some of them are kind of straightforward. You would probably think of it beforehand, but it's just to point it out easily. And then the other one just tells you an electrical tip. So that might involve a certain electrical connection to make, specs for a certain device. Yeah, so it's just to hopefully make it a little bit easier to see throughout the slides. All right, so first we'll be kind of talking a little bit about sensors. I believe this is the complete list of sensors we have available. I think I didn't include the LiDAR, but that someone else is going to go over in detail in another lecture, because that's really just a USB device, and then you have to do stuff on your machine to actually make it useful. The same goes with the webcam, the first thing on that list, which I think, is just another USB thing you'll plug into your NUCs. If you guys have sort of been familiarized with the computer you're using, the Intel NUCs. And then someone will go over how to actually run software to use the webcam data. But we have a selection of infrared distance sensors, time of flight variation of the infrared sensors, eye view, color sensors, and micro switches, which are, if you guys have heard of limit switches, it's sort of similar. I think micro switches is a more appropriate name. They're just mechanical switches to be able to tell the position that a body is moved in order to normally use to signal a stop or something. Yeah, so really quick, we got the long and short range sensor, IR sensors, which in general IR sensors work by firing beams of IR and then measuring that back through a receiver and sort of measuring it at an angle and calculating the distance from that. The wiring is actually pretty straightforward. You'll see a typical IR sensor with sort of in that form factor. It's got 3 wires coming out of it, reds for power, blacks for ground, yellows for signal, good stuff. Yeah. So you likely won't be using these for, I guess, anything the LiDAR can do itself, but you might be able to use these for more internal situations on your robot. So a distance sensor for an effector you're using, or some other mechanism, whatever it might be. Just know it's available. And the power requirements are also there. Most of the sensors you'll be able to power with 3v3 or 3.3 volts, which you can source off of the TNC, which we'll also go over. This is the microcontroller development board we'll be using. Yeah. So, also, I should probably mention, feel free to interrupt with any questions if you want. I'll probably try to go a little bit faster with the sensors. Ultrasort are a variation of the IR sensor. You just have a binary output. Same power requirements. You could power it straight from your TNC, from your microcontroller board, and it can be used to detect motion of some sort. Time of flight is a fancier sort of version of the IR sensors we've been using. These are just some details about how to communicate with it. You'll get more into the nitty-gritty about that when you get to use the TNC and the microcontroller. Yeah, same power requirement, and it says here. It may take a little bit more time to figure out how to actually implement this, but there are plenty of tutorials online. In a bit, I'll have links to the actual devices, so you can look them up and search through documentation for any guidelines or something like that. And you can also ask questions. Also got a color sensor available. This detects RGB components, as well as a couple other things. Pretty fancy. Yeah, it's 3v3 voltage, and a little bit of detail about how to connect that. So you connect the input to the TNC3 regulator, or potentially 5 volts. Yeah, well, I'll talk about where your different sort of levels of voltage will come from, but for now we'll just talk about the battery and the output voltage. The regulated voltage is going through like a regulator. So the regulator is the thing that converts the higher, like 14 volts and up voltage to logic level or somewhat close voltages that these devices, like your sensors, and actually some other motors will accept. So we'll just talk about them as regulators. We'll talk about exactly what the regulators will later on in these slides. Yeah, it's the color sensor. And I included a slide that has documentation for all of these. All the ones I mentioned, plus a couple others. So I didn't include slides for the IMU we're including, as well as the IR braking sensor. The IMU is I think it's like the 9250 one, maybe some of you have used before. It's pretty popular. It's a 9-dot sensor that also powers off 3v3, 3.3 volts. And there's a lot of documentation online for that and source code. And the IR brake beam is just, it consists of an IR transmitter and a receiver, and you can use that to also detect motion, maybe in a very specific way, something that's across the beam and break it. Yeah. That's good more stuff. Yeah, so if you explore any of these links, I believe all of these should have some sort of a spec sheet or data sheet where you can always find dimensions. So if you need to CAD something to accommodate one of these sensors, you can definitely always get the sizes of all holes in the placement. And that's important to consider because, as we'll talk a little bit more about later on, when you start CADing your design, for those of you maybe who haven't had much experience sort of combining the mechanical and electrical side of things with CAD, you've always got to keep in mind the space taken up by like housing for electronics, form factors of boards, electronic boards, all that kind of stuff. But this is putting it out there so it's sort of fresh in your mind when we get to it. All right, so that's about it for sensors. I'll just go over and talk about actuators now. Just a reminder, again, if you already interrupt me, ask questions if you have any. So we have a bunch of 50-to-1 geared motors, which are really just like ordinary DC motors with a gearbox inside. And we have variants that have built-in encoders. So the encoder is just the sort of black attachment on the back, or actually it's behind it. on the back of the motor. And the wires coming out of it are running from the encoder into the motor, so you can make encoder measurements, or measure the encoder's measurements, and run the motor also. For those of you who are not familiar, maybe an encoder is used to keep track of how many sort of revolutions the motor or some sort of spinning body, I guess, takes. Talk about a little bit about how it works, but it's a really useful device, and there are libraries out there that apply to specific encoders, and so you can know how to use them. Yeah, recommendation. That's the thumbs up right there. These motors that include the encoders, we recommend you use as the main drive motors for your robot. So things that'll drive its main wheels. So you might see them on the kitbots. You might have already seen the kitbot. And we'll also have, like I said, the versions of these motors without the encoders. If you need to use something with like the same torque spec for the vectors anywhere else on your robot. So yeah, the connection is actually for the motor. It's red and black. It's to power. Oh yeah, question.
I was just wondering
How many of the motors we got? I think we ordered the encoder versions we have 112, so that's 2 per team. Yeah. And then we have some other without the encoders. Like these. 2 per team. 2 of the encoders, and depending on what you guys decide to do, you can get 1 without the encoder. The power for the motor comes basically directly from the battery, which is 14 volts and above. Just as a note right now, that 14 volts should not go anywhere else that's not the motor. It'll go to a motor driver, controller board, but not anywhere else, because 14 volts and digital logic don't mix very well. Yeah, I was already talking about the encoder on it. There's a wire on this device specifically for you to just hook it up to 5 volts from a regulator, as we talked about earlier. I think also USB power. I'll have to see about that. I would just recommend using a regulator for now. Yeah. Connection table for your convenience. Yeah, the Polu website page for this motor, we can also send that out. It contains the same details and probably more stuff in case you guys want to send it out or something. Yeah, really quick about how the encoder works. Those who are curious, they basically have this magnetic ring attached to a shaft on the other side of the motor, so the other side opposite to where the main drive shaft is. And there's a board right underneath it that includes a couple of Hall sensors that can measure it at different points in time. And so the wire is basically you're powering it and you're reading from your Hall sensors to detect whether the magnetic ring has passed this point in the PCB or this point in the PCB. From there you can determine distance and speed traveling at speed. Yeah, and all the sort of details are in this slide. I'll kind of just skip the slide for now, but as I said earlier, slides will be available for y'all, so you can look at it. It's kind of what I said, just with a teeny bit more detail. Yeah, and that's kind of goes along with that. Okay, so the actual motor that we're talking about is going to be routed to the motor controller board run by Citron. Motor drivers in general contain pins that you can solder to, or maybe screw terminals that you can connect wires to. And there will be pins to accept some sort of square wave signal, we also call it PWM signal, that essentially controls sort of the average power delivered to the motor, and in effect can also influence the speed of the motor. So there's just like a 0 to 5 volt logic PWM signal going on somewhere on this board, and you have to connect the motor inputs to another part of the board, and that's how you get the motor running at a speed you want. So it's adjustable by voltage, by PWM. Yeah, I'll use this for both your motors, and there's some specs which were chosen pretty well for the currents you'll probably see in your robots, and except I think 2.5 voltage pretty nice for us. And you can also switch direction motor drivers also include pins and logic that allows you to change the direction of current flow. Yeah, so this is a diagram for motor wiring. This is kind of outdated. In that diagram, you'll see a PIC microcontroller on some sort of breakout board. Again, we're using the teensy as our sort of the brains, the low-level brains for the robot, at least, to run the motor driver. So it'll be pretty similar. We're using the same motor driver, and essentially you're just routing some the PWM signal pins and probably one digital pin on the teensy to control the direction of the motor control. Yeah. And yeah, that's essentially how to do it. For more detail, we can send out the actual like product page. They also say the same information on how to do it. For just to sort of start on the safety aspect now. Don't wire up the battery into both reverse polarity. That's an important one. Yeah, because certain circuits are meant to work in one direction, but maybe not the other. Because if you switching polarity kind of reverses current, and that's almost never good for any circuit, especially on the motor board. I'll have to get back to you about this connector because I'm not sure I've seen it. Yeah. That's just a bigger version of the wiring diagram. Important note, just don't reverse polarize your battery. Just gotta emphasize that. Alright, so now we're talking about servos. Maybe some of you use servos before. They're pretty good for pretty good application for your effectors. So like manipulators or anything like that. Normally they're pretty good for the job. They have built-in closed loop position controllers. Some even have for control, which is pretty cool. But yeah, you want to choose one that's right for your application in your robot, whatever factor you're choosing to do. Yeah. But just keep in mind that the servo has a limited range of motion. Normally goes sort of zero from wherever it was, like, I don't know, started to 180 degrees. It's limited mechanically. And yeah, so the servo, you're going to need a regulator to convert your battery voltage down to 6 volts to power the actual servo as a separate power supply. And then the input will be routed to the teensy, to the microcontroller board to control the actual position of the servo. So you can use PWM square wave signals to change between 0 and 180 degrees. There are libraries on to do that. And if you've used Arduino before, oh yeah, sorry.
You said due to perfect collision software modules be provided to us by you guys, or?
Actually, I believe so. Eric, can you chime in on that? Because
what was
we were
that?
talking earlier and about what we have in
like spec sheets for the servos?
Selecting servos, do we have servos?
We have. So you can go upstairs in the lab, and then you can see the ones that we have in stock. I believe we have the spec sheets for them, but you said they weren't on the website? Is that your question?
No, I just wanted to know if they were being provided to us, or this is something that came with it.
Oh no, the servos are provided.
Thanks, sir.
Yeah.
Just one final note, make sure it's only the yellow wire from the servos. I guess I can't necessarily guarantee that it's the same color scheme on the servos we have, but generally they're pretty easy to distinguish. Sometimes the ground is brown, sometimes it's black. And the signal, which would be yellow or it's mainly yellow sometimes, most of the time. That's the only wire that you want to run to the TC for like external control. Yeah. Okay, so we got sensors and actuators sort of in discussion now. So let's talk about power and where your power comes from and how to sort of distribute power, regulate power, all that important stuff. All right, so this is a table with general power breakdown for your robots. Yeah, so notice motor controllers and the NUC are getting powered directly by your battery. Powering your servos with the regulator, a step-down converter, and also a buck converter. We'll get into the details about what it is later, but it's just your regular power your motor encoders. We talked about 4 or 5 volts. A lot of sensors can also work on 5 volts. Maybe some have internal regulators that can convert 5 to 3 if that's what they're into. Or 3 to 3 for also most of your sensors. Yeah. So you'll be powering the TNC microcontroller board through your NUC, and that has an internal 3.3 volt regulator that can very likely source enough current for a lot of sensors. Well, the sensors we talked about earlier. Yeah. And I guess I'll get to where on the TNC that is. Yeah. So, you'll be using LiPo batteries to power your robot. Yeah, basically everything is going to be your life juice. So there's already a sort of slot on the kit bot for it, but if you're kind of deviating from that design, just make sure you have some sort of a combination for the battery. You want to make sure it's nice and cozy in your robot, because it's the really important part and also the most dangerous part. So when it comes to charging your LiPos, they consist of, they're like 4 cell series LiPos, so they have 4 cells with like max voltage of like around 4 volts. So when you charge them all, they need to be balanced to make sure they're discharged and charged at the same rate. It totals around 60 volts. Yeah, so it's very important to charge your batteries as much as possible to conserve the life of your batteries, to sort of not hinge on the death of discharge and all that good stuff. Yeah, and charge, and never let it fall below, I guess, this sort of rough threshold, around 14 volts, 14 and a half volts. We have low voltage alarms that do just this task for you. So you plug them into the sort of wires that come from the individual cells on your battery to make sure it's all balanced, and also to make sure you don't fall below this threshold, because that's like the danger zone for at that point it might be overly discharged and you'll see some problem. Yeah. So all of our work is happening over in 38500. I think you guys already went there, and we'll have chargers, like actual battery chargers for you guys to use. They plug into these adapters to the wall to charge them. So I think the charging will be happening there. Hope that answers your question. And I'll go over how to procedure to using one of those chargers in these slides. Good question. But yeah, there's also danger of overcharging your LiPo. That's also danger zone. So that's why you don't do things like leaving charging overnight. You don't just want to forget about your LiPo charging. If it's charged enough for your application, then it should be good. It's really dangerous. Your LiPo is no joke. Yes. I just wanted to raise my voice a little bit for that. As you'll see in this kind of short video. Yeah, you don't want that happening to your LiPo. Keep it safe. And I'll talk a little bit more about that. Keep it safe. But yeah, I just played it again because I like it. But yeah, it's not a good thing. Alright, so don't discharge your LiPos too far, as we were just saying. Don't discharge them too far, don't charge them too far. You don't want to leave them in places where they could overheat. Some of you guys might be carrying your materials around in one of your bins, like a kit. You just want to make sure if you're handling the LiPo, make sure it's in a sort of dry, cool place. Because overheating is more incentive to do what happened in the video there. So if you want to try to cut the wires on one of the leads, I think our policy is to have students ask one of the staff members. I think in general, when it comes to cutting batteries, maybe for some people it's not the case, but for others, it's sort of like a hard lesson learned to not, for example, use a pair of wire cutters to cut both leads at the same time. I've heard of people who sort of went through that ordeal. But yeah, it's probably better to just have someone be told about not to do that, than as opposed to them learning that the hard way. I feel like, it's probably the more pleasant way. But yeah. If your LiPo starts to pop up, the one in that video was a really complicated pop, but even before then it starts getting a little fluffy. If you feel it like starting to pop up, like notify a staff member. In some cases it might still be you don't have to start it necessarily, but in a lot of cases it starts becoming pretty dangerous. So yeah, make sure you tell staff members if it does that. Don't charge overnight. As I was saying earlier, or always keep a watchful eye on your LiPo if you're charging it, so be around it, because we don't want fires to start. And always use the balance charger, which I guess we'll talk about in a sec, to make sure the cells in the LiPo are charged and discharged all at the same rate, and to avoid damaging the battery. Yeah, so now on to charging safety using the charging devices. So when it comes to charging, so you'll get the 70-watt adapter for AC that sort of looks like a laptop charger. And on it, I believe, Eric, is there some toggle switch or something for you to actually make this setting?
Yeah, it's an adjustable power voltage output. And so you want to set it to the 16 volts when you're using it for the charging application.
Thanks. Yeah. Make sure you do that. And if, at any point, if you have any questions, even after I go through the slides, like right after or when you're dealing with LiPos, please don't hesitate to ask. We want to make sure everyone's safe. So we have Poppy King LiPo balance chargers, which are kind of just like stations. So plug in your LiPos into, and the AC adapter we're talking about just plugs right into that. So this is your source of charging power. And then the balance leads to the LiPo, which I believe are the individual cell leads, should go onto the charger itself. That way you'll charge the individual cells. And then the balance charger will tell you exactly how much you charged, so you know when your LiPos are ready to be taken out. Okay, general discharging safety tips. Whenever it's not charging, have the voltage alarm I mentioned on it. I think I have a picture of it somewhere, but it's like PCB with a pin header on it, and these 7-segment LED displays that tell you how much voltage it's detecting. It'll sort of like scroll through the individual cell voltages, and it may tell you like the total voltage. Always pay attention to that, and always have that plugged in if you're using your LiPo. It'll notify you pretty well if you're going below the threshold. Okay. Over discharging is the extreme case of discharging. If you forget to recharge your battery and you keep discharging the cells, at some point that battery is going to be damaged, kind of like irreversible damage in a way. And at some point it should probably be discarded. So it's in cases like this where the LiPo can start getting puffy. Generally no good. So let staff know, any of us know if something like that happens. We understand mistakes here and there happen. It's part of the learning process. Just really do this. Okay. So this is the regulator we've been talking about. It's the DC-to-DC buff converter, also known as a switching converter or a step-down converter. It's called the step-down because it converts a higher level DC voltage down to a regulated lower another DC voltage. And for that reason, they're pretty useful, and they can be pretty sturdy, have pretty good current ratings. And so you take one of these boards, it's like in my hand right here. You want to take probably like a flathead screwdriver or something like that, and you turn this like knob on that blue component, which is like a variable resistor, just in the neat form factor. It's called a tripod. So you just turn the knob, and if you hook it up to a power supply, you can see the output voltage adjusting as you turn the knob. So you want to set it to what you want it to provide for whatever subsystem of your robot you're using it for. And I would recommend, I would say, like maybe every day you work with your robot, just check with a multimeter. You guys have used one of those the output voltage of your buck converter. Depending on the buck converter you use, the output voltage may drift. This is safe to make sure you're supplying the right amount every time. But yeah, I think in Maslab experience, I hear they've been pretty good about that. So it's always good to be safe and check. Yeah, some specs. You can see the output voltage range goes from like around 1 to 35 volts, so you can power anything in your system very likely. But it has a current limit of around 3 amps, like that's recommended. So that's why if you're connected to a lot of servos, for example, like these ones here, you want to probably use 2 step downs if you're using it for any other motors also. 2 step downs to sort of distribute the current between the 2 converters. So it's sort of be like a power battery source, and then it's sort of hooked up to two regulators or converters in parallel to make sure you just stay under that current limit to be safe with the converters. Other than that, the 3 amp current limit that you'd be getting from these converters are well over enough for powering your TNC and other sensors. Although you won't be powering your TNC, it's powering them with the NUC. Like right now, TNC intro. Okay. So if you guys have heard of TNC before, or Arduino actually, it's a very similar platform. In fact, from my experience, you can open up the Arduino IDE. You just download a package called TNCguino to make these work, and you write the same modified C code and run it on TNC to do stuff. You just have more versatility. You have a lot of pins capable of doing several things. So you have some like ADC, so analog digital converters on there, PWM pins, communication, like serial communication pins, and like the stuff you would find on Arduino. It's just on a smaller form factor, and it's actually faster. Yeah, and so there's some online tutorials on PGRC. That's the manufacturers for these boards. I just had the link there. You just go to the website and you find a bunch of information on it, like right off the bat. Yeah, don't solder these straight on. So the TNCs, you first have to solder pin headers to, and some people might be inclined to just solder that straight onto like a proto board or whatever they might be using. I think most people might be using breadboards, but in case you're using a proto board, just don't solder directly. Use these female headers that are basically like sockets for the male headers that you would place on the TNC to just like slide it to and lock in place. So you can swap one out in case it burns out or something. You fry it by mistake. Yeah. So use sockets. Solderless jobs are more like temporary. Get better for prototyping. Yeah. Power it with the NUC. It's a micro USB cable. Then just generally be careful with using it because they can be easy to fry. Yeah, this is kind of here for your convenience. You can look at this whenever you want. You could also just probably type into Google TNC 3.5 pin out, so pin out for I/O, and you get the same exact diagrams indicating where the different pin utilities are. So you got a bunch of PWM, digital and analog pins. Yeah, the whole deal. Okay. Thought it might be good at this point to sort of combine everything we've been talking about so far into what will sort of look like an example setup, an example diagram representing all the connections you'll be making. So sort of at the top of the hierarchy is your battery, it's like the king, and then you're directly powering your NUC with the battery. This is a refresher. The motor controller, which will be driving your motors. You'll be feeding the same voltages into like your converters, your step-down converters to bring it down to lower voltages to use for your other stuff. And it sort of just trickles down to everything else we've been talking about. To the motors, auxiliary motors, servos, whatever you will be using. Yeah. Okay. Now, talk a little bit about the electrical design side. So this includes not how to design circuits per se, because it's kind of like the ballgame, but just how to think about your electronics in terms of your overall design. So it's maybe like system level view, how will it affect the CAD. You want to make sure there's no space. Make sure it's easy to integrate and assemble, disintegrate, and then reassemble when you really need to make a change or some sort of things, especially in competition day, that comes in really important. So we'll talk about that. But first, why not blow up your electronics? Like, you know, it's kind of a thrill, right? To just blow up some electronics. Well, why you shouldn't blow up your electronics is because the more you fry, the more like components you fry, maybe a mistake, maybe you know, will be more hesitant to buy replacements. So we want to make sure you guys treat the kits you got and the components we already have with respect. And if you're about to do something you're wondering about and you're not sure if it'll like work or if your component will come out safe in the end, feel free, don't hesitate to ask questions to make sure you're doing the right thing. Yeah, so we have a limited number of spares, and we can order more, but yeah, I like this saying, if teams break too many, we will be sad. Yeah, sure. Yeah, our understanding that mistakes happen. Again, it's a learning process. You know, don't take it like super seriously, but just be respectful of the parts and just know that know that it's important not to just blow through a bunch of parts and components. Yeah. So when it comes to success and failures, what do they look like when you're building your robots? So the two most important ones in this list up here are in the red box because they're important. So always use your low battery, the low voltage battery monitor. So a little PCB to stick on your battery to make sure the levels are charged to which one and that you don't over discharge. And include fuses. I'll talk a little bit about fuses in the next couple of slides. But fuses essentially are like bulletproof safeguards against overcurrent. Maybe you've heard of fuses in like a household. They protect against like, overcurrent, discharge. Essentially just like kind of like a switch in your circuit that blows up if you get too much current. That's how it's designed. Include switches to separate different power rails or different devices from being powered. Color code your wires, of course. Take some over here. Label everything. So if a certain device needs like 5 volts or 6 volts, or if you just want to label like your different rails, your power rails, so 5 volts, 6 volts, the battery voltage, you can use like some tape or labels to make sure you can easily identify different things on your robot. It also makes it easier for like say one team member is working specifically on the electrical routing. Someone else can easily identify like where to find a certain thing. So labeling is very important. Using key connectors whenever possible. So these are connectors that are specifically made so that you don't accidentally reverse polarize things. Yeah, so we have a bunch of those for you to use. But yeah, just take advantage of them. So make sure that no one accidentally, maybe they'll sleep deprived or something, even if they've gotten down the technique of like correctly plugging in a device to a battery or something. These key connectors are really good safeguard for that. Make sure it doesn't happen. Yeah, so you want to insulate anything that's exposed with some heat shrink or electrical tape, preferably heat shrink. And yeah, if you think you've kind of tried a small component that you think this doesn't work, but you have no 100% guarantee to looking at if it works, just get a look at the component if it's like small enough. Then likely we can probably replace it somehow. Some ways to fail. Talked about a lot of this already. Reverse polarity or voltage, too much current, short circuiting. Watch your connections, make sure they're not exposed, and just like not the short circuits everywhere. Bad connections, so this can be from like bad solder joints, which happens a lot, especially if you haven't soldered before. It's kind of a common occurrence. So yeah, just I guess when you make a solder joint, my sort of pro tip is to go ahead and check the continuity with the multimeter right after to make sure it's decent. And then there are some signs that tell whether a solder joint is not good or it's good or not good. And you can like find info about that online. Yeah, use switches to separate power from different things, your motors, your microcontroller, some other motors you're using. Yeah. Alright, so real quick, so the fuses. So the actual fuse is in this picture. You see that like green thing up there? It looks like a chiclet, like a gun or something. That's the actual fuse. And written on them are like numbers that indicate the amount of current they'll withstand before blowing up. So this one is rated for like 30 amps, and they're also color coded. And we'll be using 10 amp rated ones, and they'll be red, but this is just an example. The fuse, you just want to place it into one of these sort of like black enclosures. We call them fuse holders. So you just slide them in, and that sort of ensures that the terminal and the fuse are connected to those two wires coming out. And so you want to make sure that the fuse holder, the wires on the fuse holder, are in series with and immediately after the battery output, so that all of your current will sort of go only through the fuse holder. Now, just to make that clear, I'm going to draw a diagram real quick. So this is like your battery. Okay. And then this is like ground, right? The positive terminal of your battery, you're going to want to route directly to that sort of wire on that fuse holder, the little enclosure, and then the fuse kind of goes inside, and then the other end of the fuse holder goes to wherever else it needs to go to power some bunch of robots. So it's immediately right after the battery. And so it's just that's the fuse holder. Just thought I'd just make that clear. Immediately after the battery in series. We also have wires and connectors that you can crimp. Crimping is just attaching connectors to wires that are paired. So you can make variable size connectors, sort of like those header connectors, to accommodate whatever you need to do for your various connections you'll be making. So here are some pictures that sort of illustrate good examples of organization with routing and labeling, and good choices made when incorporating electronic components and design. The one on the left sort of has a switch band for separating, powering different aspects or different parts, different components of the robot, which is always a good sign. And also you can see that the wires are really neatly routed around different areas. Bends like that are not that hard to do. Just take a pair of pliers and kind of bend your wire. Makes it pretty good. Labeling is like masking tape is good. It's got to label stuff. This is a more, I think, complete picture of the same robot. So you'll see the same things. Well, maybe some things are a little bit frayed, but wires are labeled, color coded. You'll still see the switch band, and there's also like the switch terminal up here, the green screw terminal, which is just basically like a housing with screws on it, so you can like screw wire into. Preferably use like solid core wire to make sure the connection's right. It's just a mechanical connection that becomes an electrical connection. So that's a sort of short summary of that, and I'm happy to answer any more questions about it too. The space taken up by your electronic components, it exists, and you need to really keep it in mind. I know when I was starting out with sort of just building stuff in general, I may have forgotten, what's the board layout, or what's the form factor of the board or motor controller I'm using. I would just end up like hot gluing it in place. That's no good. You want to make sure you accommodate for the form factor of all of the components and make sure your robot is nice and neat. You can reach in for things, swap things out as needed. Generally, this becomes your friend in the end. It's really useful to think about these things ahead of time. I should mention our power distribution buses. I think this is kind of a tip, but also maybe a little bit mandatory. They're just really good ways to break out your different voltage rails, power rails that come out of your regulators. I think we'll be distributing some in your kits. I even have some extras available. We'll definitely. Just think about all of this when you make your robot chassis. And I think we really want to slide. So that's all I have for today. If you have any more questions, feel free to ask.